Hi everyone and welcome back to the Zoyam Academy channel. This is part 2 of a series of videos on MRAC, which is the Model Reference Adaptive Control for first order systems. So in part 2 of the video series, we will go over the derivation of adaptive control for first order systems. We will consider a generic first order system with a reference model, and we will also determine the control law and adaptation law, including the analysis of the stability of the system. And so we are going to take 12 general steps, right? Starting with control, defining what the control system is, and picking a reference model that we want the plant or the control system to follow. And so we will also define an ideal control law and use that substitute that ideal control law inside the control system model to get a closed loop dynamics. And then we will use the idea of model matching conditions to, since we're trying to drive the system to the control system to the actual plant to follow the reference model. That is how we are going to get model matching conditions. And from that, since we know that the parameters are not always perfect, so we define a new estimated control law, which is actually the same as the ideal control law, but just estimated control parameters. And so we will take that estimated control parameter and then substitute that again inside the plant model to get a closed loop dynamics with an estimated control law. And we will now use the model matching conditions that we determined earlier to update the closed loop dynamic, essentially just to refine the closed loop dynamics in order to be able to determine the error dynamics. And then we will use a lemma that allows us to formulate the error dynamics in a certain way that we can determine the adaptation law. And lastly, we will use the Lyapunov stability theorem to determine the stability of the control system. So without
Hi everyone and welcome back. Let's continue with part 2, which is on the derivation of the adaptive control of a first order system. So to get started, we are going to first define what the actual plant model is, right? And essentially the reason behind adaptive control is that we don't always know exactly what the plant model is, right? We can just estimate what it is. And so basically for this derivation, we will consider a plant model of this form where A and B are the constant plant parameters, and essentially U is a control input and X is a state vector. Now, in addition, we will consider a reference model, right? Essentially, the idea behind the reference model is we are saying, okay, we want a plan to follow essentially how the reference model is doing. So if the reference model is doing good, then we want you to follow it that way. If it's doing bad, we still want you to follow it, right? No matter the condition, we still want it. So in this scenario, we are defining a reference model of this form, right, where you have AM and BM as the constant plant parameters. Now, RT is essentially the reference signal that we want the model to follow, both models to follow. So it can just be basically a trajectory that you want the system to follow. And so the next step is we define an ideal control law of this form, right? We define again, you can define your ideal control law whatever way you want to define it, but again, you got to pay attention that it's gonna work, right? You can't just define anything and expect it to work. You have to. Sometimes it takes trials and error to figure out, okay, what is the ideal control law that I can use for this problem. But for this specific problem, we are going to use this form. And this block diagram essentially right here just shows you essentially what this controller is kind of doing, right? It's basically taking the state vector from the plant and then just feeding it back to the system, right? It goes through different gains, the kx gain, which multiplies the state vector, and then you have the kr gain, which multiplies the reference signal. Now, kr and kx both are variable parameters, which we are going to talk more as I go down. And yeah, and then you have the error, right? The error essentially taking the state vector from the reference signal and then subtracting that from the actual plant to get the error. And the idea is we want this error to go down to 0. And to do that, we have to make sure that the parameters in the plant model are equal to the parameters in the reference model. That is the best way, that is the main way to, or the best way I would say, to make it happen, to make the error go to 0. You have to make those two be equal, right? Okay, so now the next step is we go and to determine the closed loop dynamics, we substitute this controller that we just assumed, right? That this is the best controller that we think it's gonna work. That we are going to substitute that back into the actual plant dynamics, right? And so basically this is U right here, and yeah, and essentially you do the derivations and you get this is the new plant dynamics, right? This is the new plant dynamics. Now the next step is, like I mentioned earlier, we want this error to go to 0, and so how do we do it? We want these two models parameters to be equal, and to make that happen, essentially you just do, right, this guy, which is this guy right here, equals to AM, which was the reference model plant, right? You remember? And then you have this BKR, same thing right here, equals to BM. And then you have these two control parameters. Now, one key observation is that since A and B are unknown, the control input will achieve these objectives adaptively. Essentially what we mean is the adaptation law that we will determine later on will basically every time step it's continuously trying to search for those right gains, right? Because again, you don't know what the right gains are, but so every time you try to like adapt and determine those right gains, and to determine those right gains you have to use the tracking error. Again, more on that later as I dig a little bit deeper into this. So now we have the ideal controller, but again, we don't know what the right gains are, and so we have to consider a controller with the estimated gains, right? That is basically the idea behind defining this second controller. The first one was, okay, we know perfectly what the gains are to make the system track perfectly, but in reality that's not always the case, right? So we do have to consider the estimated gains, and so what we do is we do basically kind of what we did earlier when we determined the closed loop dynamics. We essentially substitute equation 6 inside the plant dynamics, and after you do a few substitutions you will get the same exact equation as the previous closed loop dynamics. The only difference is now that kx is kx, that's an estimated control parameter. Same thing with kr. Now what we do next is we are essentially trying to the next step is essentially using the matching conditions that we obtained earlier from equation 5, and what we're trying to do is we're trying to rearrange x dot, which is the new plant system, with the estimated control parameters. Essentially what we're trying to do is we're trying to rearrange it in a certain form where it's going to help us determine the adaptation law. And essentially what we do is, again, from equation 5, this is nothing new, this is something we've already derived earlier. You basically just rearrange things, and then you can represent, you can also represent BKR RT in this form, right? This is exactly the same thing, because these two guys can cancel out and you still get the same thing. But we want to represent it this way because this is key, right? What you're looking over here is we are taking the difference between the estimated parameter and the actual estimated control parameter and the actual the ideal, I won't say actual, but ideal control parameter. This is going to you're going to see the effect of this later on. Now, so again, like I said, what we're basically just doing is doing the different substitutions to get this new control system dynamics, right? Again, you can see it has this delta kx, right? I won't call it delta kx, but I will call it something else, but it takes the difference between the estimated and the ideal control parameters. And so basically what I just mentioned earlier, again, you know, the parameter errors are basically defined as the difference between the control parameter provided by the adaptation law and the ideal parameters. And essentially what it's really just saying is this is how I'm going to represent this guy, right? It's basically going to be kx tilde and kr tilde. And then basically that's what you get there. And so you basically just make that substitution. So I mean, this equation is basically the same as this one. The only difference is you now use this to simplify the equation. Now, the next step is to determine the adaptation law. And to do that, we are going to first start by defining what the error is. Again, error simply defined as x minus xm. And then the error dynamics is you basically, the reason why you have to differentiate is because, you know, your system is represented in x dot form, right? So you have to take the first derivative. And so x dot, basically we're using again equation 8, right? That has the estimated, that has the difference between the estimated control parameters and the ideal control parameters. And again, this is equation 2, which is our reference system, reference model. And what we do is we basically just substitute those two into the error dynamics, which, you know, you do a bunch of substitution and bunch of simplification, and you will end up with equation 10. Now, this next step is critical, right? And essentially, if you in Slotin's book, there's a lemma that says that, again, I'm not going to go over this proof, I'm just using it. Essentially, it says that it basically gives you a lemma that is used in the determination of the adaptive laws of MRAC systems. And essentially, it considers two signals, right? It considers two signals, E and psi. And then they are related by this equation, where E of t is a scalar output, H of p is a strictly positive real transfer function. And you have k as an unknown constant with a known sign. And again, psi of t is basically an m by 1 vector function of time. V of t is basically a measurable m by 1 vector. Now, the idea really behind this is you want to have your error, this error that we obtained earlier, that we obtained right here, you want to change equation 10 into this form. And if you are able to change it into this form, then you can say that your adaptation law is going to be of this form. Again, I'm not going to go into the proofs, but this is something that everyone uses. So I'm very sure if everyone is using it, then that means it's working. You don't need to go into the proofs of this. But just the main idea here is you want to convert your error dynamics into this form, into equation 11 form. All right, so again, you can go more into this, and I'm going to put the reference to that to where you can look at that lemma. Now, so like I mentioned, all we need to make is equation 10 to be in the form of equation 11. And so what we do is we just rewrite equation 10 into this form. Now, if you remember how to do Laplace, to use a Laplace operator, this can save. E dot is simply the same as SE, where S is the Laplace operator. And then you have the AME, and then you factor out E and do a few substitution, and then this is what you get, right? You get E equals B over S plus AM times that, which, if you take a good look at it, it does appear to be in the form of equation 11, right? Let me just scroll back up a little bit here. Let's just memorize a little bit what we have here. So we have H of P, which is a positive real transfer function. Again, transfer function, that's why we had to use the Laplace operator. And then you have this term inside the brackets, which again, if you look at it clearly, you're going to see that this guy is H, and then this one is basically what is in the brackets. So yes, we can affirmably say that yes, our error is essentially in the form of equation 11, and so we can define our adaptation law to be in this form, right? Again, the adaptation law, remember, is the control parameters. I mean, not the adaptation law. Yes, it is control parameter. It's updating the control parameters, right? Nothing else, just the control parameters. Again, MRAC is very powerful because you can also use it to update the system plan parameters, not just the control parameters. But for this case, we are just using the control parameters. So I hope you have a better understanding on how to get the adaptation law. Again, all you have to do is and the reason why we obtained this error is because of how we determined our control law, the ideal control law, and the estimated control laws. Now, let's move on to analyzing stability. Now, to analyze the system stability, we use Lyapunov theory, and for this specific example, we will use we will use a Lyapunov candidate of this form. And, going through the Lyapunov theorem, if you get V of 0 and then you get V greater than 0 for all these parameters not equals 0, then that's good. And then when you take the derivative, as long as this guy is greater than 0, the idea here is we want this V dot to be less than or equals 0, which is going to be the case because E is always going to be positive, AM is positive, and so you're always going to have V dot be less than 0. And so we can confirm that the system is globally stable. Again, it's globally stable because we don't have any restrictions on the control space in some sense. And so in final, we determined what the control law is and what the adaptation law is. Now, in part 3 of the video series, we will go over briefly solving a first order system and also programming it in MATLAB in part 4. And I hope you guys understood something from the derivation. Again, it's a very simple derivation. If you do it a couple of times, you will understand what's really going on. I'm going to try and see if I can upload this to the YouTube or to my website. All right, thank you.